All right. So, today we are going to talk about a topic that is more software oriented because this is 142, right? So we want to let you feel the connection between composing software and the hardware architecture. So the topic we are going to talk about today is that how to be a performance programmer on modern processors. But before we start, right, it's always a good idea to remind ourselves what modern processors are. So not too far away from the lecture today, we have been talking about superscalar. So the idea of superscalar is that previously we mentioned we only have one pipeline, but we have a lot of hardware resources actually in your processor. For example, you have multiple of LUs that ideally you are able to run like branch instructions and LU instructions together, or LU instructions and memory instructions together. However, because of the hardware design doesn't allow us to do, so we don't have the capability. So to fix that capability, that hardware is called superscalar. And superscalar's concept is really simple. So instead of just fetching one instruction around, you see two arrows here because we are fetching two instructions or more than one instructions at a time in general. And then once we also need the unit that support decoding for more than one instructions, and then concurrent access of registers because you want multiple instructions to get their operands ready at the same time. And also together with the data forwarding logic that we have, right? So that's the superscalar processor. But superscalar, they still have to execute their code in order. So it turns out there are many chances that we might be missing in getting a better use of your hardware units. However, because the stupid ordering thing, so the head of line blocking issue is actually preventing us from use the hardware more efficiently. So we have a set of optimizations which I summarize everything in this slide. So basically, a modern processor now, they must have these three things all together. So the very first thing is superscalar we have talked about. And the second thing is that to enable out-of-order execution, we actually have register renaming logic, which avoids the false dependencies in our code, as well as a dynamic instruction scheduling unit, which look over the data dependency has been resolved or not in the instruction in the queue. Why I just feel like there's something wrong. Why am I like spending so much effort talking today? Because I forgot my microphone. Okay, so so you have register renaming, which is the main reason why we can do auto-order scheduling by redirecting the output of an instruction to a physical register, which is not visible to the programmer, but only used internally to temporarily store the outcome of an instruction. So with that, we are able to avoid the false dependency problems that we have seen before. And then you also need the logic to redirect the inputs from those temporary outputs to the instruction. And then with that, if all inputs operands are ready, which means that all the input register have the value that is already produced in the physical registers, then you can actually go and execute your instructions. However, once in a while, you might have issues, for example, branch misprediction. So you cannot actually have your result presented to the programmer or in general, the rest of the system if a prediction result is undetermined. So if your instruction is executed under the case that we are on a predicting path, then that execution is called speculative execution. And because we are speculating the execution path of your program. So to support speculative execution, you need a reorder buffer, which is a place that can buffer all the results of those or the status of all instructions that are still not 100% certain yet. And then once we figure out something is wrong, we can flush their results. So that's the current way how we deal with how we run programs right now in your processors. So it turns out you will have to have additional logic to perform register renaming. You also have a reorder buffer like I draw here. So that's the pipeline we have. And again, you might think, well, and again, right, to figure out how efficient that we can use register renaming hardware plus auto-order execution, I don't want you to really dive into the detail regarding how to draw a pipeline diagram. And think about the nature, right? The nature of register renaming and auto-order execution is that we want to execute your instruction whenever the output, the inputs of an instruction is already generated. So in this way, all you need is a data dependency graph plus some restrictions on the issue with. For example, if you can only issue 2 instructions, just make sure that in this data dependency graph, you don't have more than 2 instructions put into the LU or memory unit and a branch at the same time, right? Then this is how you figure out how many cycles it takes us to issue all these instructions, which means that how many cycles we can put this instruction into execution. And through this analysis, you can learn quite a lot of things. For example, if you observe and if you draw the data dependency graph with the alignment of the issue width properly, you can figure out, pretty much, right, your execution is following the same path in a way that it takes 3 cycles to execute 5 instructions, and then you can divide that number to get an average CPI if this is a loop that you are going to run for a long time, right? And you also know that, okay, other instruction that doesn't matter a lot, only the instruction on the critical path, which is 1, 6, 11, 16, 21, this instruction, right? Every 1 plus 5 an instruction for this example would determine the execution time. So those are the critical path instruction in this execution. And who are on a critical path instruction is actually, for this example, is actually the move instruction, right? So you know, okay, it also reflects our observation because memory operations, they are so long nowadays, right? So if you really want to improve the performance of your processor, improving the memory performance would be the first key. So that's why we start with memory optimizations. And so that's pretty much what you learn from this, right? And another thing that is interesting, right? The reason why we can get 0.6 CPI that is lower than 1 is because we have the instruction level parallelism that has been exploited through superscalar auto-order scheduling. So instruction level parallelism means the parallel execution among instructions from the same program. And as you can see, like this instruction, they are all from the same running program instance, which in your operating system class, this kind of running program instance is called a process, right? So within the same process, I found instructions that can be executed in parallel. That's called instruction level parallelism. And you see in this data flow, data dependency graph, we see many cycles we do exploit that kind of parallelism so that we can finally got a CPI that is 0.6, very close to 0.5, which is our optimal CPI for a 2-issue pipeline. And however, you know, if you are a programmer who doesn't know this and you just use your own imagination, your raw expectation about your hardware, and you think, I just want to use those fancy data structures that I learned in CS100. And turns out I put linked lists in many of my code. Then this is what you get, right? From data dependency graph analysis, you know that, well, the CPI is only 1 on average, right? And some of you might be questioning me, right? What if I have a processor like Intel Alder Lake that has a lot of wide issue pipeline? Because you might think, well, the issue why I only have 1 CPI is because you only restrict the number of issue widths in the processor, right? But what if I have a processor like this, or then I should be able to get better CPI, right? But if you look at the code right now, what I'm assuming that is that, okay, that's lifted the restriction that you can only issue 2 instructions at the same time. Instead, I allow any numbers of instructions to be executed right away once we resolve the data dependency. You still see, right? Like the best case, we can only issue 3 instructions at the same time for this piece of the code. And the average CPI is still unchanged, right? So that means that if your programmer doesn't really care about what each instruction would take to execute on your computer, you are not or you don't have the concept of instruction level parallelism. You are going to create program, even we have the best processor, which has unlimited number of fetch issue with plus unlimited number of functional units, you're still going to suffer from the very low CPI, very high CPI, very low IOP problem, right? So today in the lecture, I'm going to teach you about, I will give you some example, and from that we can feel, if I want to be a performance programmer, how should I compose my code? But before I start, right, again, as I told you many times, right, I don't know how many of you play Pokemon on like, what was that, Switch or DS before, right? But you must know that, well, how many of you have played that game before? Pokemon? Okay, not a lot. Okay, or you don't want to agree with that. Okay, any fine. But if you want to be a Pokemon master, right, you want to know every Pokemon you own pretty well so that you can strategically choose the right Pokemon, the right attack to use every time, right? So it's very important. And same thing, if you want to be a good programmer, by good programmer, I mean performance programmer, good performance programmer, then you must know the beast, your Pokemon, which is your processor, very well. So from what you have learned so far, can you discuss with your friends? Okay, so this is not a random question this time. I want you to remind yourself and talk with your friends. What are the characteristics that you learned so far about modern processors? Discuss with your friend. This is a review. Right timing. Oh, it becomes quiet so quick. What do you guys have in mind? What a modern processor will look like? What are characteristics do you think a modern processor would have? Okay.
A lot of ALUs.
A lot of ALUs. Okay. What else? So to use those a lot of ALUs, what other features do you think the processor will have?
A scheduler.
A scheduler, pretty powerful scheduler, right? And but without what, we cannot do that scheduling. Without something, we cannot do very effective scheduling on using those hardware. So scheduler, functional units, what else? Are these 2 good enough? You need memory. What kind of memory? Okay, multi-level caches. Okay, part of it. What else? Program counter. Okay, that's the basic. What else? What do you think a feature that modern processor would have?
Kind of mentioned this, a lot of built-in parallelism with like each processor is actually multi-core that has.
Okay, multi-core. Okay, that's a separate topic, right? But how about each core? What? Pipeline. Okay. multiple LU pipeline and scheduler. And okay, to use those multiple LUs, right? You say there's a scheduler, but without what? Even though you have a scheduler, you are still having limited capability of using your hardware. What was that? We spent a lot of time talking about it. Fetch and decoding in what way? Multiple instructions at the same time, right? The ability to fetch and decode multiple instructions, and that is called superscalar, right? So we talk about superscalar, we talk about auto list scheduling, we talk about cache. What else? There are something that we talked earlier today, but not mentioning. So register renaming, right? If you have a powerful scheduler, but if you don't have register renaming, it's not going to work out very well, right? What else? What? Data forwarding, okay, that help us to save a few cycles. What else? Branch prediction, right? Awesome. So these are all the stuff that we can see in modern processors, right? So we have multiple LUs, we have multiple functional units, we have multiple load store units, we have multi-levels of cache, and right now we have been building the cache in a way that is multi-layered, and there are even prefetchers that make the hit rate really high, so that if your code has very good locality, right? And we also have predictors with very high accuracy as long as your code is predictable. And the predictor may be like perceptron based or variable history length, right? So those are the features of modern processors. So today we are going to talk about, with these features, how are you going to program? How are you going to program on those hardware? So, well, you know, I know a lot of you like LeetCode, so I try to rephrase the way how I describe my question. So today we are going to start with a program called pop count. So pop count is the full name is population count. So if you give the program a number, it will tell you how many ones are there in the number. So this is very useful. So for example, if you want to design error correction code, parity check code, you need to know how many ones and zeros are in your number. And if you want to do cryptography, right, you also need that. And sparse matrix multiplications, you also need to know where we have numbers and the intersection, where are we going to get result produced. So that's also useful. You also want to get fingerprinting by counting how many ones are there. And also, if you want some and sometimes we use big factors to implement some kind of data structure, and counting how many ones are there are also important. So this is a very important problem. And so that's what I said, the LeetCode style, right? So if today I give you a 64-bit integer number, I want you to find a number of ones in its binary representation. For example, if I have a number called 59487, and the output would be 9, because its binary representation is something like this, right? And then there are 9 ones here, right? And the driver of that is pretty much like, okay, if today I have this many numbers, and then I will call this pop count function many times. And the question today is that how are you going to implement that pop count, right? So you might have a few implementation in mind, but these are the 5 that I can come up with. And I want to ask your opinion as a performance programmer. Which one do you think that would perform the best on modern pipeline processors? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so we have two answers that are exceptionally being supported and also a diverse opinion about A and E. So why don't you guys discuss with each other to see what do you guys think is the right answer? It's not working. All right, let's wrap up in 15 seconds. Hello. Five, 4, 3, 2, 1. Time is up. Okay, so after discussion, more of you think it's C now. So can I hear some of your opinion about why you picked that answer? Like, which one do you think would be the best performing and why? Anyone want to try? Anyone want to share his or her or their opinion?
So all of them are correct, right?
Yeah, they are all correct. Otherwise, I won't list them here. They are all valid solutions for pop counts.
So I was definitely thinking it's between C and D.
Okay, why?
So we're using a table to really
Mhm.
avoid like a data dependency between X and is now depending on to adding to the C.
Mm-hmm.
Now I believe the compiler can optimize that X and OXF
Mm-hmm.
to like have there be a less data dependency. So that's why I think it's between those two.
Mm-hmm.
And then I changed mine to C from D because I noticed that we're actually shifting 4 over and we're depending on X, whereas I originally put D because I thought for loops seemed like they're performing better on grade scope than while loops.
Mm-hmm.
But
on gray scope, then while loops.
yeah, I don't know.
Okay, you don't know why, right? Okay. But it actually works for you, right? Okay, so here's the thing, right? The lecture today is very important to your lab 3, right? If you don't know where to find solutions, today's lecture is probably the most relevant. But okay, you said okay, so but you think C would be faster. Why? Why depending on X would be faster?
Well, you pointed out that actually the for loop is going to run too many times because we're shifting by X, and if they're both correct, I think D would run more iterations than C.
Okay, is that what you guys were thinking about? Okay, so sometimes demo is really important, right? So that's why we love demos. And that's why you need the class, right? So if you get the right answer, I guess you probably shouldn't take this class because you already know all the details. But right now I'm going to show you the demo. And The result might be a little bit surprising to you. Let me see, where's my mouse cursor? Okay, here we go. So we have done this code example, right? And this is the pop count that I have. Okay, here's the thing. Okay, let me run all to save our time. Restart kernel, and let's run all. So, oh, you know what? One problem was run all. Okay, so this is the linked list example. And okay, we have this pop count program, right? And this is version A, right? As you guys see. And and now this is version B, right? Exactly the same as what I gave you. And this is version C. We have a while loop. And the biggest difference with version C and D, there is a for loop compare against while loop. And version E, we have a lot of case statement, right? So if you are a software engineering oriented people, you probably like this implementation a lot, right? If you are in 110, that's what they ask you to do, right? But let's see what the performance of each would be. So so here I ran it several, I ran each one with time. So we know how much time it takes for each one, right? And so now I start running like A, B, C, D, E, and let's see how much time it would take. So for A, well, so I click a button of run all in this cell, right? So that's why it runs through the beginning to the end. Don't do this in your lab, by the way. You're supposed to do it one by one, okay? But if you really want to save time, that's probably the easiest way to do. So the thing is like, okay, let's look at version A. It takes 22 seconds to finish. And now look at version B, 12 seconds, right? So from version A to version B, we got almost twice speed up, right? Are you satisfied with it? Actually, never, right? So let's look at version C, which is also a popular answer, the most popular answer. Indeed, a lot faster than B, right? 5 seconds, right? Version D, 3.7. What's going on there?
Is it because there's data dependency on condition?
Okay, we will dig into that detail later, but let's just remind the result. So far, D is the best, right? And let's look at the one that teachers like to teach you when you are in your CSE 8A or 110, right? What is that? Wow, right? That's the worst, right? So don't trust those people who teach software engineering. They don't really know how to do performance programming. So, this result, isn't that surprising to you? Isn't that surprising to you? Counterintuitive, right? The easiest, the most readable code actually turns out to be the slowest one, right? And the naive implementation is even better than that, right? So why is that? So we do want to dig into the detail by each, but right now, all you need to know that, okay, version B is faster, right? So in your lab 2, lab 3 assignment, if you figure out that, well, there's some way I can do it like this, right? So there were students asking, oh, I cannot get speed up, like how to deal with those leading zeros. And I try to tell you, right, how you can only have a maximum of 10 to 11 digits, right? What does that tell you, right? You can actually have a for loop, right? Don't use a while loop, but for that case, right? But there's a reason for that, right? So let's look at the reason why each version is different one by one. And that's actually pretty reflective to what you have learned in modern processors. So why B is better than A? All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, looking at, woohoo, I love this graph, right? It means that we want to talk with each other. So why don't you go ahead and talk with your friend for 90 seconds and let's see what's going on. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, more of you think it's B now. So, which means that you guys agree one of them is correct. Okay, so let's play one thing. Can you guys say that one statement that you have in mind that is correct? And I will count 3, 2, 1, and you all say that number together, and let's hear if that's the same one. All right, 3, 2, 1. Okay, 3, 2, 1. I originally hear a 4. Where does that 4 go? Okay, what do you think? So you said we can say again?
Like B is doing it 4 times.
Uh-huh.
So maybe
So we are doing this like, so it's pretty much like loop unrolling, right? So we unroll a loop for 4 times. So what are the potential benefits do you imagine that we can do?
maybe I think benefit more from renaming
Renaming.
and digits as like 4 registers.
Okay, we can treat each digit as 4 registers, right? So
Then you can
right. So here's I bet you must see this. Four, right? It looks like we do have data dependencies. However, we can temporarily store this 4 axis into different registers, right? And if you do that, we are actually breaking up the dependency chain, right? So we potentially can have fewer data. Do you guys agree with that? Okay, and a lot of you believe it's 3, significantly fewer branch instructions. Why is that? Why is that? Why we have significantly fewer branch instructions? Right. So in the past, we have, if you have 64 digits, and if you're unlucky that every digit is not, well, the number is a really large one. It takes you 64 bits, right? Then the worst case, this one would execute like 64 times, right? But for this one, it's 16 times. All right. So that's why you have fewer numbers of branch instructions. Agree? Okay. So I would say this time, let's look at that. So it all goes down to how we implement the code at the assembly language level. I know a lot of us hate things at the assembly language level, but sometimes in performance programming, every instruction counts, right? So let's look at that. So for version 8, this is the assembly code looks like. So for each iteration, it's pretty much like this 5 instructions, right? So this is where the LCX is, right? So we have an iteration that goes for whatever times that you have in your digit, right? And then, so we pretty much have 5 times an instructions, right? For the number of iterations that you need. And if you are having this, right? I can say like on average, I'm going to do like n divided by 4 because iterations, because I have 4 iterations on row here, right? So this is the instruction sequence that I end up generated through the compiler. So I didn't mock this up. This is all generated by the compiler. So if you look at these pieces of code, there might be something you think very odd. So for example, like why this is NL1, this is 2, this is 3, this is 4, right? So, as some of you, like as you pointed out, right? The compiler nowadays is really smart. They look over this, right? And they look at this. This is, so then they do some kind of constant propagation. So if you took the compiler class, a lot of compiler people, they are really good at discrete math and mathematical theory because they can conduct that, okay, if I concatenate this with this, then I will end up getting like this is shift right 2, this is shift right 3, this is shift right 4, right? So although we do see there's a potential of data dependency, but in fact, when you compile the code, if you do an optimization called constant propagation, right? Or the strength reduction, you will be able to see, well, and where do you learn this? Lab 3, right? So if you go through your lab 3 carefully, you'll figure out this compiler optimization is pretty common. And if you enable this optimization, then turns out this data dependency will be gone, right? So that's why you see this 1, 2, 3, 4 come up and with a shift instruction. So this is not this one, right? Well, no, not that one. You don't have to, yeah. So this one. So the thing is, so the thing is that, right? This would help to break up the data dependency chain and allow instruction level parallelism. And the other thing that we only need 1 branch for every 4 iterations. So we reduce the amount of branch instructions, which potentially, right? If you have a branch misprediction that you have learned, right? It would take like 34-ish cycles to recover from that, right? And given you only have this amount of instructions in each iterations, right? Then that's probably a branch misprediction probably worth more than that. So if you can reduce the chance of getting branch, that's actually going to help the performance a lot. So in terms of instruction count, right? Because right now we have 15 instructions over 4 iterations. So on average, each iteration has only 3.75 instructions. So you are going to reduce the dynamic instruction counts a lot. In addition, you also potentially get some data dependency result because you have this hard-coded 1, 2, 3, 4 in shift, right? So that's how you actually get better performance. So I would say, first of all, right, one thing that you guys forget is that if we have significantly lower number of branch instructions, it also means that we are going to reduce that dynamic instruction count. First one is correct. And the third one is also correct. And fourth one is also correct. So the answer is actually D, right? And the only thing that is not correct is probably 2, right? Because for both pieces of a code, you are only going to miss once at the very end, but you just don't know which one are you going to miss, right? Sometimes it's the 64th, sometimes it's the earliest one. And but saying that each number you only have one chance to miss, right? And for this one, it probably took longer time for you to get a miss. But for this one, it's quicker for you to get a miss. So in terms of miss rate, this one is probably higher than the version A, right? So that's why 2 is not the right answer. And if you don't trust me, let's see what the performance counter would tell us. So that's wrong. Let's look at the demo again, and let's scroll down to the performance counter part. Okay, so later on, after getting the time profile, I start use perfstat to get the result. But how come I don't see the perfstat result getting printed? So what if I run perfstat A and B? It would take about 40 seconds from what I can tell. So let's give it some time. Give it some time. Give it some time. Sometimes, here we go. So, okay, so for pop count A, right, here we see it takes about, let me see, can I have a, okay, doesn't work out, okay. So it takes, if you look at the instructions, number of instructions we have here, it takes 332 trillions of instructions. And the number of branches is actually 65, right? So as you can see, like every 5 instructions you are going to have a branch instruction, which is pretty much similar to the code that we have seen, right? And among the 65 trillion branches, about 724 million are branch misses. So the miss rate is already pretty low, right? As you can see, it's probably like at the level of 0.1%, right? And let's look at B, right? So if you remember the number, right? So it was 332, but now as we reduce the amount of branches we have, right, it's 287. And the number of branches also goes down from 65 to 17. So it's pretty reflective to what we count roughly in terms of dynamic instruction count. And the branch misprediction rate here is also, let me see, this is probably 0.5%, right? Okay, 0.35%, right? So it's actually slightly higher than the version A, right? So you know the misprediction rate is not going to be better. But because we have significant reduction well, we have fair amount of reduction in the instruction count. Plus, if you check the instruction per cycle, right? So previously with version A, because we have data dependency for among each iteration. So if you look at the number of instructions that we can execute per cycle, it's only 2.89. But right now, with this pieces of code, with the compiler optimization, it's going up to 4.5, meaning that you are able to have almost like 5 instructions in execution, which is pretty good, right? And given you remember this is an Alder Lake processor, so you have 5 LUs that you can execute in concurrently. So this is pretty much use up all the LUs you have, right? So this is actually meaning that in terms of using IOP, it is doing a really good job. Okay, but why is this not the best performing? Why is it not the best performing? Why even the implementation of C is better than B? So that's the question that I want to ask you. Why is C better than B? So for this question, the answer is 3. Why is C better than B? Yes.
Curious. So I noticed the instructions are like open. If we were to like do all the X's and all the, oh, I guess, right. We're just thinking if that would change.
Well, if you have more registers, if you use more variables, and if you are 100% for sure those variables can go registers, that's effectively the optimization that your compiler would do, right? Okay, 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. Oh, okay. This time we have a pretty unanimous answer of C. So what is C? So, okay. So what are the two that you guys have in mind that might be the answer? You put 1 and 4. Okay. Other ideas? So 1 and 4. Other ideas? What? You also think 3? What else? Anyone advocate for 2? Okay, so for the 2, why none of you think it's the right answer? Because it's pretty much the same, right? We do it every 4, right? Right. Okay. So how about A? Has lower dynamic instruction count than B. Is that correct? Why is that correct? Mm-hmm. Mm-hmm. Okay, so to implement this iteration, right? So you remember we need 15 instructions for that, right? As we think, right? But can you imagine how many instructions we need for this? Okay, we need 1 shift here, right? So that's 1. Okay, we need an and here, that's 1, right? How about this plus equal? That's 1, right? And how about the table access? That's another 1, right? So how many? 4 instructions, maybe 4 or 5 instructions, right? Plus the branch, right? Okay, isn't that significantly lower than B? Right, so you have fewer instructions. Okay, how about the misprediction rate is the same, right? The same amount of branch instructions. How about data hazards? Should be pretty much the same, right? So if you look at the answer that I will put, right, is pretty much, right? First of all, right, only 1 is the right answer, right? And if you don't believe me, right, again, like, let's take a look of the profiling result, right? So remember, we already have B in mind, and let's run C, which takes a little bit of time. So let's run C. Okay, let's run C. I think I should have run E at the same time. Is it running C? Okay, let's run C. I would run E as well. Okay, so this is C, right? So for C, okay, remember previously in version A or version B, we have 200 trillion, 300 trillions of instructions. Right now, it's only 102, right? A huge reduction from what we had before. And the number of branches is still 17 trillion, which is very close to version B, because by default, there shouldn't be any difference, right? And the branch misprediction rate is about the same, right? So that's where we are. That's where, so the hugest difference between version B and C is because we have significant reduction of number of instructions. Okay, so I do have a question, a separate question for you, although it's not a pop-up quiz like this one, but I'm curious. Okay, so why is this one? Why is B better than A? Okay, so we now know that C is better than B, but without what architectural support, the code of C won't work. We have been talking about many features of modern processors, right? But if we don't have what, it won't work. If you don't have cache, right? So lookup table, they are relatively big, and it's typically bigger than the number of registers you have. So you can never implement a lookup table in a register. So you have to put them in a memory, right? And if you have to put them in a memory, and don't forget, the memory access latency is about like 100 cycles or even more in most cases, right? And if you have virtual memory support, which most of the cases you do, you also have to bear the risk of TLB misses, right? So it's a huge cost if you have a lookup table in a memory in the past. But right now, if we have a cache, which can store a small amount of data and with relatively fast access time, right? So thinking about this, right? So here we take 15 instructions, right? And although some of them could be executed in parallel, right? But for 4 iterations, it still takes roughly like 4 or more cycles to execute, right? But with this one, right, if your table is small enough, we can actually put them in a cache, and each of this would take 4 cycles if cache hit, right, in a processor. And some of you might be arguing that, okay, 4 cycles, it sounds longer than this, right? But if we have good instruction level parallelism. But don't forget, if you remember, your hardware also have the capability to access multiple memory locations concurrently. You have pipeline memory access unit. Even though each of this take 4 cycles, as long as this table entry doesn't rely on the previous table entry's result, then you can still parallelize the memory access, right? So that's why this whole thing together make lookup table, small lookup table, a good alternative to replace these things. Get it? But on the other hand, if you don't have the hardware with good enough cache, if you don't have the hardware that can parallelize the execution of memory unit, code C is going to give you worse performance. So this is only valid because we have cache and concurrent or say parallel memory access units. So that's why it's really important. You know that we have this feature, you know that we can exploit that, right? So for this question, there's only one answer correct, but the reason is not because instruction count makes things happen. It's also because it doesn't take too much time to execute that instruction because we have the architecture innovations goes on. All right, so the most mystery one is why D is better than C. Why do you get, why is that? All right, wrap up in 15 seconds. Five, four, three, two, one. Time is up. Okay. Choo. Okay, a lot of you think the answer is B. Let's do something fun together again. Okay. If you guys all think there's one thing right? So after I count 3, 2, 1, tell me what's that one thing right in your mind. Okay, 3, 2, 1. See, we see a lot of different numbers, right? So I hear 2 and 4. What else? Okay, so first, do you guys think we are going to have lower instruction? No, why not? Because because this is a for loop and we are going to run it for 16 times every time, right? So, but this one has while, so there's a potential the loop will terminate earlier. So it should have higher instruction count. What else? So 2, significant lower misprediction rate than C. Is that correct? Okay, because it's very regular, right? But for the while loop, I don't know, like if I should terminate at 16, 15, or even 1, right? Because every number is different. But for this one, it's pretty regular, very easy to predict. Okay, so you think 2 is correct. How about 3? Fewer branch instructions than C. It has more because we have to always run it for 16 times. But again, for this one, it may terminate earlier. That's what you saw. How about 4? Data hazards? What do you guys think? Okay, data hazard in a while condition. So using 4 is correct. Okay, again, let's run the performance counting stuff again, and let's see how good are you on the route of being a performance programmer. And this is A, B, C. Wait, why the C didn't show up this time? Let me save it. I wonder if it's not saved. Okay, let me run B and E as well. And but in the meantime, okay, so look at C, right? So for pop count C. So let's try to put them all together. Okay, so the upper one is C, the lower one is D. So for the upper one, we have 102 trillion instructions. How many instructions do we have here? 80 trillion, fewer than version C, right? I have more loop iterations logically, but how come I have fewer instructions? Okay, how many branches? So on the top, we have 17 trillion. Here, we only have 1 trillion. What happened? You guys know what happened? So misprediction rate, 0.70%, 0%. But that's predictable, right? But how come? Constant propagation? That's not the right term. What else? What else do you have in mind? Can you believe that? Right? So that's why you need to take this course, right? This why B is better than C. Okay, let me explain to you. Again, we have to think how the compiler will generate the code, right? So we have a fairly intelligent compiler right now, as long as you give the compiler sufficient amount of hints. So if you write your for loop like this, what do you tell the compiler? I'm always going to run this 16 times, right? And if you are the compiler, if you know this is the amount of times that I will run it every time when I call this function, what kind of compiler optimization do you have in mind that would happen? It's actually on the title, right? Loop unrolling. Okay, so if I do loop unrolling, what I end up generating is an equivalent code like this. Looks very stupid. It makes your static instruction a lot, right? So you are actually going to unroll your code pretty much like this, right? But with this, what would happen? You need a branch. So you don't need a branch instruction, right? You don't need a branch instruction. And look at this, right? Do you remember the optimization that we have done in version B? Do you guys remember that? Right? We manually modify the shift 1 to be 1, 2, 3, 4. The compiler can do that again here, right? 4, 8, 6, 12, 16 until 64. So is there a lot of data dependency? The answer is no, because the compiler make that change, right? And you were asking me why I still have that 1 trillion like branch instructions, right? It's actually coming from the fact that if you remember the driver code, right? We call this 1 trillion times, and we have to run this 1 trillion times. That branches are actually coming from here. There's nothing to do with that pop count, right? So in fact, in this pop count code, there's not even a branch exist. There's no branch here. All branch instructions are gone, right? So what it ends up with is, okay, we do have lower dynamic instruction count because loop unrolling, we eliminate all branches. And because if you have no branches, how are you going to have misprediction, right? Because you just don't have branches, right? And then no branches, right? Again, no branches, right? And fewer data hazard and C, about the same or fewer, right? So I would say for this particular question, 3 are the obvious answer. For 4, we have to check. But the interesting thing is that for 4, for modern processors, because we have this register renaming capability. So although on the code side, there may be data dependency showing up, but the register renaming can actually dynamically resolve it. So I won't categorize that as the main issue. But for this particular one, why D is better than C, right? These 3 statements are very surprising to you, I know, right? But in this end, you start to have a feeling. If I want to be a performance programmer, experience really matters, right? And that's why in our lab 3, we give you a lot of experience in how compiler is going to optimize my code. So my conclusion here for version D, right? A few things that you can learn here. As long as you give more hints to the compiler can do a fairly good job to optimize the code for you. And what are the hints? For example, can you make the number of iterations be predictable, right? So like this one is totally unpredictable. But if you make it predictable, then the story would be different, right? Okay, so now the last question, why is E the slowest? It's the same option, but I want to cheat a little bit because I'm worried that, okay, let me run, let me see if the previous result of D has been saved because I do need their result. And I want to run it. Okay, apparently it's not saved. Oh, all right, never mind. So it seems like there are some issues with that. So let's vote on this question first. Let me know what do you guys think in 90 seconds. All right, let's wrap up in 15 seconds. Why is E the slowest? 5, 4, 3, 2, 1. Time is up. Okay, I like this graph because it means that we have to discuss. So why don't we go ahead and discuss with your friends for another 90 seconds and let's see what you guys think. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay. After discussion, oh wow, the power of peer instruction. A lot of you think it's D. So, but before we run it, before we know the answer, right? Let's look at what perf would tell us. And it's pretty strange that today it doesn't save my result. Okay, so let's run D and E. And D takes very short period of time to run. So so now we can imagine it takes us about a minute to finish this. And you know, sometimes I feel like being a talk show like player, that was really hard because like at this period of time you have to keep thinking about what to say before before something happened, right? So yeah, what can I say? Like a minute. How are you going to kill in a minute? I don't have a joke. And the best thing about like watching a talk show is that you find they have a lot of politically incorrect jokes that you should never talk in lectures, right? So that doesn't really help you a lot. You know, I have been trying my best, but it hasn't finished, right? So, but, oh, here we go, right? Okay, so number of instructions we have is 173. It's actually not the worst, right? So it's actually not the worst one, right? And the number of branch instructions is 44 trillion. It's actually fewer than the 67 of version A, if you remember that, right? So what actually happened? So I know this result is difficult for you to compare. So I actually summarize everything. So this is version A, B, C, D, E. So forget about the last one. For version A, B, C, D, E, right? This is the instruction count. So E doesn't have the worst instruction count, right? So one thing that you must remember here, right? That's why a lot of you, when we talk about MDOS law, you were saying about why instruction count is not reflective to the execution time. This really tells you, right? It's all on the same processor, the same machine, but instruction count doesn't mean anything here for the performance D and E, right? So E has or like B and E, right? So B has more instructions than E, but turns out that the performance of E is worse. And it's really because of the CPI or IPC, which is the reverse of CPI here. Or in another way is the amount of instruction level parallelism that you can execute. And it turns out it's only 0.61, which means that you have 5 LUs, but with this pieces of code, only less than 1 LU is being used. And why is that? And the reason is because if you look at the branch misprediction rate, it's actually 6.8%. That's a lot. But you will have a question, right? So why, right? If you look at the code, right? If you look at the code, right? If you look at the code here, right? Yeah, we are doing exactly the right thing, right? The for loop here is pretty predictable, right? What's going on? Which branch is not predictable? The switch case, right? So a lot of people would think, okay, it's very elegant that I write switch case to make my code more readable. But here is the code that what would actually generate it to reflect the switch case. So the right-hand side is the implementation of the switch case. And I do a little bit of the color code here so that you can figure out which is which. So for the ones that I put like 1 here, right? Oh, this is actually the, so for the +1 cases, right? The compiler is still do a fairly good job in group them together. So for those ones, right, they are actually L10 block, right? So you can see we have an at L1, right? And jump to L5. And for those two, they are actually this one, the L9 block. For those three, we are actually in L8 block, right? And for +4, we actually are in the L6 block, right? But what really makes the switch case really bad is because the implementation of the switch itself. So for the switch statement is depending on the output of and F. However, how we implement that is actually a jump instruction. And the jump instruction is depending on the result of RCX. And for the RCX is actually, they have a pointer here, right? So this pointer is actually an index in this jump table. So if you look at this jump table, it's actually telling you, so this is L7. L7 is the location of this non-track right next to the jump instruction. And this is actually tell you the offset. So it's actually telling you, if you see this index, then how many bytes do you have to jump? So it turns out like I have L5 minus L7. So it means that if it's a case of 0, then I should go to L5, right? So if it's 0, right, that's the default case, right? So I go to L5, and which is exactly right because it's shipped right by 4, right? And if it's 1, then I should go to L10, which is exactly the case 1, right? So this is a jump instruction. However, what's going to be in the jump case is totally unpredictable. Agree? Because we have 16 different potential. And this 16 different potential, they will jump to 4 different places. So where to jump is actually very hard to predict. It makes things very hard to predict, right? So that's why switch case is a terrible idea for this pieces of a code, right? So it turns out the reason is because we have the highest misprediction rate. Other than that, it doesn't really have the most branch instructions. It doesn't really have the highest dynamic instruction count. It doesn't really incur the most data hazard, simply because of the branch misprediction. So if you can write your code that your processor can guess what's going on, right? Then the world will be perfect, right? So, you know, but you might think, okay, is D the best implementation? Is D the best implementation? So another thing that modern x86 processor would really like to do, right? And that's why Intel processor is sometimes valuable, because if this is a very frequently used instruction, they would the frequently used algorithm. They would try to make it a hardware instruction or put a hardware accelerator on your processor to have it. So, for example, right? Because pop count is such an important instruction. So, the recent extension in AMD and Intel processor, they actually have a pop count instruction. So if you code this like intrinsic, right? And if you compile your code with this flags, the compiler would actually generate code with that hardware acceleration. So this is the resulting code, what it looks like. It's very ugly, I know, right? But let's look at the performance and you will figure out like if this is a function that you run a lot of times, right? So far, the best performance we get is probably 3 seconds. And as what I just mentioned, right? As if you are running a company, right? Every penny counts. So if I just need to modify my code to be a little bit ugly and it will give me better performance, are you going to do it? And the answer is that a lot of people would do, right? And let's see how fast it runs, right? I just click at the button not far away. It only takes 1.57 seconds, which is twice speed up over the best version that we ever get so far, right? So that's the value of hardware acceleration. So being a programmer, sometimes it's really important for you to read a spec of your underlying processor, knowing what are the good instructions that could be used. And then you can produce the most efficient code for your application's purpose. All right, so I think we have a pretty sharp on time for the lecture today. And, not too many things I want to let you know before you leave the classroom, because since it's close to the end of the summer session, we only have 1 more week plus tomorrow, right? So assignment 4 due this Sunday, and it's already on the website. And I think Leon is going to give you a discussion session later today to teach you how to solve the question. And it's only 1 question this time, although we have a lot of sub questions for that 1 question. But but it shouldn't be bothering you too much if you have been paying attention to our lectures. And we also have lab 3 due tomorrow. Okay. Other than that, enjoy the rest of your day. I will see you tomorrow.
Yeah.